spooler directory. Okay, you put your files to be printed in this spooler directory. Okay, you copy your file to this directory. Anybody can copy the file to this directory, and there is a daemon called, okay, special daemon called spooler. The spooler daemon is a background process. It runs all the time. It checks if the directory is empty or not. If there is a file in the directory, it sends that file to the printer. Okay. So whoever puts their jobs, their print tasks on that directory first is served first. There is a priority mechanism, but you can handle that using different kinds of mechanisms. But there is a priority handling mechanism too. So this spooler runs at the user level. It doesn't run at the kernel level. Okay. So the kernel level is here. There, kernel is here. The spooler, although it's part of the operating system, it runs in the user space. Okay, so there is not much to talk about actually about the user process, because we have been doing this all the time when we are writing programs in C or C++. Any questions about the user level software? Okay. Then we talked about this chapter. Remember, in this chapter we talked about the hardware aspects of the I/O, then the software aspects of the I/O. I just completed it. Then we are going to talk about specialized I/O devices like the disks and the clocks and the user interface devices, etc. And we will start talking about the disks. Disks are just one of the I/O devices, but they are so common. We use them all the time, and we need to look at them more carefully. So these are two disks being compared. Okay, this one is from the original IBM PC from 1985. Okay, and this is a very new one. Okay, this is a floppy disk actually. This is 360 kilobytes of disk, and this is a 300 gigabyte disk. So we are trying to compare them. So what has changed? What has changed in 30 years? Okay, so this is 1985, and this is okay, or maybe 84, 2014. I'm not sure, 1 or 2 years. So this has a capacity of 360 kilobytes. In those days, it was a very, very high capacity drive actually. Number of cylinders is 40. There are 40 cylinders on a disk. And this one has almost 40,000. This is almost like 1,000 times more cylinders. And tracks per cylinder too, this one has 255. What does this mean? Tell me another name for this tracks per cylinder. Number of what? Tracks per cylinder. Tracks per cylinder. It is the same as number of number of circles and number of tracks are the same, but I'm asking something else. It's a hardware. It shows the number of tracks per cylinder. Number of heads, reading, writing heads. Okay, this one has only a single disk, okay, a floppy disk. You have only one head for the upper layer, upper side of the disk, and one head for the lower side of the disk. And even those days, for some cheap drives, okay, they had only one head, okay. In that case, you had 180 kilobytes of data. You need to remove your disk and you need to reverse it and put it again, okay. So that was the case. This guy has this many, okay, 255. Sectors per track, okay, sectors per, okay, these are the, okay, this one. So these are the tracks. This is a track, okay, and these are the sectors. Each one is a sector. This is a sector, and this is a sector. Okay. So sectors per track is 9 for the 30-year-old floppy drive, and this one is 63 average. What is 63 average? What is average? Why does it say average? This one has 9. Okay. This one, I mean, there are 9 sectors for each track for the floppy drive. The other one has 63, but it's an average. It says average. Why does it say one of them doesn't say average, the other one says average?
Ortalara yaklaştıkça çünkü bizim sektörlerimiz daha küçük olmak zorunda kalıyor.
Bunda da öyle, bunda küçük, burada büyük ya.
Ya o gerçek bir gösterim değil, öyle yukarıda o kadar büyük olduğunda şey etmeyecek abi.
Şunun gibi bir şey diyorsun yani.
Aynen.
Yani her bir track'in farklı sayıda sektörü var. Dışarıdakilerde her bir sektöre daha, şuna bakın. Buradaki sektörler küçük küçük, buradakiler büyük. Aynı bilgi tutmak zorunda bunlar. Disk büyüdükçe öyle olmuyor artık, yapamıyorlar. İçeri doğru geldikçe küçültüyorlar sektör şeylerini. Yani şeylerin ne diyeyim, dışarı doğru büyüdükçe sektörlerin açılarını küçültüyorlar. Alanları aynı olmuş oluyor. Yani şununla şu aynı alanı tutuyor ama açıları, kapılıkları açıları farklı birbirine. Dolayısıyla burada 2 tane şey var, zone var. Bazen 9-10 zone'a kadar, 16 zone'a kadar da çıkabiliyor. This is the average. Okay. So sectors per desk. Test. So this is 40 times 2 times 9. Okay. Okay. 40 times 2 times 9 is 720. Okay. Sectors per desk. And this is the sectors per desk. Bias per sector size is the same. Okay. Seek time 6 milliseconds and 0.7 milliseconds. So it is like 10 times faster. 30 years, 10 times faster is not good in computer science. Okay, is not good in computer industry. I mean, we usually double the speeds in every 2 years, right? In computer industry, in 30 years of time, 10 times speed up is not good. Okay, it is not like the car business. I mean, in 1985, what was the Murat 124 top speed? 120 kilometers per hour, right? Murat 124'ün yaptığı buydu. 120'yi geçtiğini hatırlamıyorum ben 1980'de falan. Hatta 120'ye ulaşmak da kötü bir şeydi. So, in 30 years of time, bugünlerde ne üretiyor koç? Buna benzeyen. Ne üretiyor? Murat 124'e benzeyen ne var şu anda koç ürettiği? Ha? Egea diye bir şey var. Onun şöyle bir şey yaptığını sanmıyorum saatte. Böyle olması lazım 30 yılda yani. Araba işinde, mekanik işinde falan filan 10 katı hızlanma kolay bir şey değil. Bayağı iyi bir şey yapmışlar ama bizim için iyi değil bilgisayar. Niye? Çünkü 30 yılda beklediğim 2 yılda bir 2 kat hızlandığını düşündüğüm zaman 2 üzeri 15'lik bir hızlanma bekliyorum ben. 2 üzeri 15 ile bayağı farkındasınız herhalde. Baba yiğit biraz yani az değil. Eğer arabayı böyle 2 üzeri 15 gibi hızlandırsam falan filan yolda bulamazsın ona. Gideceğin yerde bulamazsın. Uzaya çıkmış falan gibi bir şey oluyor. Yok. Yani şeylerin mekaniğin problemi o zaten. Since these are mechanical devices, I cannot make them much faster. Okay. So the seek time from adjacent cylinders, moving the head from one cylinder to the next cylinder used to take 6 milliseconds, now it is taking 0.7 milliseconds. Seek time average used to take on the average from one cylinder to another cylinder on the average. It used to take 77 milliseconds, now it is 4.2. It's like maybe 20 times. This is 10 times faster, 20 times faster. Okay, rotation time 200 milliseconds, okay, per rotation. Now it is 6 milliseconds per rotation. So I think this was using maybe, this means 5 times per second, right? 5 times per second, so it is 240 RPM. So that was the RPM. So this is, I guess, this is 10,000 RPM. Very fast disk, but again, it is maybe how many times? 40 times faster. 40 times faster. So again, the times are mechanical times are not that different. Maybe at most 40 times faster. Average seek time is almost 9 times better. But the transfer rate is very good. Transfer rate is 16,000 times better. Even though the mechanism did not get very well, why do you think this is much better than the mechanically? I didn't have a speed up more than 40 times, but my transfer times are 40 times better and my capacity is up by 800,000 times better. These are very good numbers. I mean, they are not as good as 2 to the power 15 watt, right? But this is good number. So the mechanism did not increase. Mechanism speed did not increase much, but I'm creating very high capacity disks and very fast transfer rates. So what is the difference? I would expect maybe at least 40 times, maybe 100 times better transfer times or disk capacities. So why do you think I have almost million times better storage space? It is because they can put more dense data on the same amount of disk space. Okay, so they did not increase the hard disk speed much. They did not increase the head seeking times much, but let's say in a 1 centimeter squared area, okay, 1 centimeter by 1 centimeter area, they can put more data in this area in the new hard drives. They developed that material science technology. Instead of electronics or the mechanical engineering advancements, they made advancement on the unit square area density for the data. That's where the development came from. Okay, so these are the disks, and this, I mean, the software wants to see the disks like that. Okay, you have tracks. Okay, this one is a track. You have sectors, and each track has a fixed number of sectors. And I am reading those sectors and from the tracks. And I have the cylinders, and I have the tracks per cylinder. That's what I want to know. But most of the time, at the hardware level, I do this. I don't do that kind of structuring inside the hardware. I am using this kind of an approach to get more space. So it is the task of the operating system to abstract this information so that the user sees this picture, not this picture. We should not show this picture to the user because user writes the code for this kind of picture. So we need to abstract this picture so that the user can do his own job the way he used to. Okay, so there is related to the hard disks, there is this concept RAID, redundant array of inexpensive disks, RAID. Okay, so redundant array of inexpensive disks. People said that these are not getting much faster. So what are we going to do? If they are not getting much faster, then we should use parallelism, right? Keep use the disk in parallel. If I store my data instead of on a single disk, if I store my data on, let's say, 8 different disks, And if I write some part of the data to one disk and the other one to the other disk and the other one to the other disk, from these 8 disks, if I read the data at the same time, then I'm getting a speed up of 8, right? So using the same technology, I am getting a very, very fast disk drive. I am getting a very, very fast disk drive. These are the pictures actually. Let's say, okay, I have 4 disks. Okay, I have 4 disks, and I am writing my some of my data to this strip 0, some of them 1. Let's say I have 8 bits of data. Okay, 8 bits of data. I divide it into 4. Okay, I divided that into 4. I write the first 2 bits here, then second one here, and the third one here, and the last one is here. Okay, so if I read all of those bits at the same time, from 4 different disks, then I get a speed of 4, so 4 times faster. That's the idea of the RAID. But they say that if you use those disks that way, let's say your hard drive can work for 20,000 hours. This one can work for 24 hours, 20,000 hours. Same thing. But if I run 4 of them at the same time, I am increasing the risk of getting a disk crash 4 times more, right? So I have a better chance of having a disk failure, of one of these disks, because I mean, it says this 20,000 hours for each of them. If I have 4 of them, there is a increased risk of having a disk failure. If one of them fails, then I lose 2 bits of data. Then all of my data will get corrupted. I will not be in a very good situation. For that case, they do this kind of approach. What they do is 4 disks storing the data, another 4 disks they are backing it up at the same time. So I am keeping 8 disks all the time. Okay. So these are the copies of these 4 disks. Okay. Sometimes people say that okay, this is both fast and this is both reliable, because I am not going to. This one fails, then I have this one. This one fails, then I have this one. This way I am increasing my system reliability too. For some cases, they don't keep the exact copies, but they write the bits on different drives. Okay, each bit is written to a different drive, but you use. Where do I have it? Okay, you use Hamming code. Do you know what Hamming code is? Hamming code? Did you hear about this? It's a data recovery actually. If you have 8 bits of data, okay, if you have 8 bits of data, represent your 8 bits of data with 10 bits. So 2 bits of redundant data. Usually the people in the communications use this technique. Instead of using 8 bits, you use 10 bits, so you have 2 bits of extra data. If something happens to some of your bits, you can recover from the error. I mean, if you are losing all of your bits, there is nothing you can do. But if you cannot recover 1 or 2 bits, then using those 10 bits, you can recover your original data. Okay, I am not going to go into details, but biliyorsunuz değil mi Hamming'in şeyini, kodunu? Network dersinde falan anlatmışlardır bir yerlerde. Communication dersi falan yok, bilmiyorum yani. Bakın, internet şeyde var falan var, kitap da anlatılmış. Web'de falan bakacaksınız, bir yerlerde var. Error correction şeyi, rutinlerinden bir tanesi bu. Hamming code. So, using the Hamming code, instead of using 8 bits, use 10 bits. And, okay, so, I have 8 bits of a byte, okay, I divide it into 4 bits, write bit number 1 here, second, 2, 3, and these 3 bits are for the having code. Okay, so I increase by data a little bit, maybe almost two times more. But if a disk crashes, or this one crashes, or two of them crashes, then I can recover my original data. So this way it is both reliable and fast. Okay, both reliable and fast. So you might say that, isn't it expensive to have these levels of these numbers of disks on the same system? Remember what does the rate said? Rate said it is array of redundant array of inexpensive disks. So these are, I mean, I am not using very expensive disks here. I am using average disks. That means that I am using maybe a few $100 worth of disks. But since I am using tens of them, maybe the whole system is expensive, but it is much more efficient. It can hold more data. Okay, it is much faster than the most expensive single large and expensive disk. So instead of using SLAC, we use RAID. You use many disks. That way, using the many disks, you have more data, you have better disks, you have a better transfer times, and you have better reliability. There are many ways of doing this. Okay, one is using the original data that way, dividing into strips, then copying them, using the having code. Again, using sometimes I can use the parity disk. Okay, this is a parity disk. What is parity? I mean, if these are my 4 bits, there is a parity bit here. So for a byte, I have 2 parity bits. If one of these crashes, then I can recover the content of that disk from